All right, everybody. Here we are, ready for the last big theorem here of the semester. So, this one concerns the divergence of a vector field. It's called the Divergence Theorem. So let's just get right to it here. So suppose we have a solid region E in three-dimensional space, and that it's got a boundary surface to it. So it's in some enclosed region of space, and its boundary is this surface S. And let's let big F be some vector field on maybe all of R3. Then the divergence theorem says that we can trade the surface integral of F along S for the ordinary triple integral of the scalar valued function, the divergence of F, over the whole region E. And so, since we're not really going to get into the sort of proof of this theorem, we should at least give you some sort of like idea behind, what it's really saying. So remember that the divergence is a function that measures at each point the sort of net outward flow of the vector field from each point. And so what this is really saying is that if we kind of add up all of those little net outward flows at each point within E, that will tell us exactly how much the vector field F is flowing sort of out of or through that boundary surface S. Okay? So, one thing that we'll say extra is that there's a couple of little extra assumptions about the region E and its boundary surface S that really have to hold in order for this theorem to really be true. But we won't have any issues with that. Every surface and every solid region in space that we're going to see in this context is not going to have any problems with any of these extra assumptions, so we'll just kind of omit some of those more tricky details. Okay, and so let's get to some examples here. So let's let E be the solid region of three-dimensional space that is enclosed between the xy plane and the paraboloid z equals to 1 minus x squared minus y squared. And let's let S denote the boundary surface of E. Now notice S is going to come in two pieces. There's this paraboloid piece, and there's also this sort of bottom like cap on the bottom here. So if we were to do a surface integral of a vector field over this surface, we would have to do really two surface integrals, one over the paraboloid piece and another one over the sort of cap in the xy plane. Like I think we saw back when we did an example of a surface integral back in, I think it was 16.7 was the section. And that was quite a bit of work there. So let's say that we're handed some vector field, big F. Its first component is 2x cubed plus y cubed. Its second component is y cubed plus z cubed. And its third component is 3y squared z. So if we were to try to do the surface integral of this vector field over this surface S, it might take up a whole lot of work. It might take us a lot of time, and I don't know, there'd be a lot of things to think about along the way. So instead, we're going to compute the surface integral of F along S by trading it for the ordinary triple integral of the divergence of F over this whole region E that's inside here. That might be a little bit easier to handle. So notice the divergence of F we can get by doing this dot product, right, of the gradient operator with F, and that gives us 6x squared plus 3y squared plus 3y squared. Oh, so that's just 6 times the quantity x squared plus y squared. Okay, and now notice that our region has rotational symmetry about the z-axis, so I might like to model it with cylindrical coordinates r, theta, and z. So when we do that, notice that we have x squared plus y squared equals to r squared under the cylindrical coordinate change. So then our function, divergence of F, becomes really just 6 times r squared. And the region E you can model, well, let's go back here. If we look at the intersection of the paraboloid with the xy plane, it happens when we have x squared plus y squared equals to 1, right? As then z will equal to 0. So that's exactly, the intersection there is exactly the circle, unit circle centered at the origin in the xy plane. right? So that'll be the sort of two-dimensional region of integration. So we'll have there that r goes between 0 and 1, and theta goes between 0 and 2 pi. And then our z-bounds start at the xy plane, z equals to 0, and they end at that paraboloid, which is now going to be written as 1 minus r squared. Or rather, z equals to 1 minus r squared. Okay, so now we can use the divergence theorem to trade our surface integral of f along S for the ordinary triple integral of the divergence of f along E. And so we've got our bounds set up now from what E was, and our function is 6r squared. And don't forget, since we changed to cylindrical coordinates, we need to multiply by the cylindrical coordinate Jacobian matrix determinant r. Okay, so that makes our integrand into 6r cubed. And when we do the z integral, we just get 6r cubed z. So we'll evaluate that at 1 minus r squared and at 0 and take the difference, and it leaves us with 6r cubed minus 6r to the 5th. Okay. And so now we'll do the r integral, and we'll integrate from 0 to 1. So what do we get? 6 over 4 r to the 4th minus 6 over 6 r to the 6th. Well, evaluating that at 1 gives us 6 over 4 minus 6 over 6. That should just be 1/2 at the end. Okay. And now we'll integrate the constant function 1/2 with respect to theta from 0 to 2 pi. That just turns out to be pi. So I think you can see that, this surface integral, if we hadn't had the divergence theorem in place, this surface integral could have taken a lot more work. And so this divergence theorem really, really is handy for trading out surface integrals for triple integrals. Okay, so let's see another one. Let's S now be the surface of the sphere of radius 2 centered at the origin. And on that sphere, let's consider the vector field big F, whose first component is x cubed plus y cubed. His second component is y cubed plus z cubed. And his third component is z cubed plus x cubed. Now, again, we're going to trade the surface integral of f along S for the ordinary triple integral of the divergence of f along the region that S encloses. So in spherical coordinates, since this is a sphere, I think it's most easy to model that way, we get that region enclosed by that sphere is really, it's like a ball of radius 2 centered at the origin. So really just the only thing that's kind of different is that the radii now aren't just fixed at 2, they vary from 0 to 2. Okay? And theta will go all the way around since we aren't specifying like some particular octant or anything like that. So theta will go from 0 to 2 pi, and phi will go all the way from top to bottom, so from 0 to pi. And notice that the divergence of f is given by what? 3x squared plus 3y squared plus 3z squared. But that just simplifies in spherical coordinates to 3 times rho squared. Ah, very nice. So then the surface integral of f along S becomes this triple integral in spherical coordinates of the function 3 rho squared. But since we're going to change to spherical coordinates to do this integral, we need to multiply our integrand by the spherical coordinate Jacobian matrix determinant, rho squared sine of phi. So our integrand becomes 3 rho to the 4th times sine of phi. Okay. We'll do the rho integral first, and we get, 3 rho to the 5th over 5. When we evaluate that at 2, we get 96 over 5. Okay, now we will do the phi integral. Well, the integral of sine of phi is minus cosine of phi. And so we evaluate that guy at pi and at 0. We get here what is minus 1 minus 1, which is 2. Ah, okay. So then we have the integral from 0 to 2 pi of the constant function 2 with respect to theta. So we'll multiply 96 by 2 and then multiply everything by 2 pi. And that comes out to give us 384 pi divided by 5. Okay. So that one wasn't so bad either. All right, let's have a couple more now. So let's keep that same sphere that same surface S from the previous example. But now let's consider this weird looking vector field here. His first component is arctangent of z. His second component is natural log of x squared plus 1. And his third component is 7 to the y. Oh gosh, this one looks scary. But notice that its divergence is 0, right? Because the derivative of the first component with respect to x is 0. The derivative of the second component with respect to y is 0. And the derivative of the third component with respect to z is 0. So a surface integral of f along this surface S can be traded for the ordinary triple integral of the divergence of f, otherwise known as the zero function in this case, along this region E. Well, the integral of the zero function along whatever the region is in question is a nice closed and bounded region. So this integral will be 0. Okay, well, the divergence theorem really saved us there, right? I don't know how to do this surface integral just from first principles, or I wouldn't really want to, right? But when you employ the divergence theorem, it becomes very, very simple. All right, so then one more. So let's keep S as, again, this same sphere of radius 2 centered at the origin, same from the previous two examples. And now consider this vector field big F, whose first component is minus y, his second component is x, and his third component is z. Notice that the divergence is going to be just this last, is just going to come from this last one, right? Because we'll have 0 from the first component, 0 from the second component, and then 1 from the third component. So the divergence of f is the constant function equal to 1. So that means that the divergence theorem will tell us that the integral, the surface integral of this guy f over that sphere S is really equal to the ordinary triple integral of the constant function 1 over that ball of radius 2, right? Okay, but remember, one of our big morals from this semester about integration was that the triple integral of the constant function 1 over some region of three-dimensional space computes for us the volume of that three-dimensional space, right? So really, since we know that that region E is just that, it's that ball of radius 2 centered at the origin, sort of solid ball, then this surface integral is just going to compute the volume of that ball. Okay, and so if you recall the formula for the sort of volume enclosed by a sphere, the volume of a solid ball, that is something like 4/3 pi times the radius cubed, you can compute this surface integral without actually doing any integration at all, right? So we know that that ball had radius 2, so we compute that this becomes 4/3 times pi times 2 cubed. That becomes 32 pi over 3. All right. Now, if you don't recall that volume formula, the triple integral is still pretty easy, I think. You'll just set it up using the same bounds for E that we used in example 2, and then make sure to multiply the function 1 by that spherical coordinate Jacobian matrix determinant, rho squared sine of phi, and you will come up with the same answer at the end. All right, so that does it for our big theorems for this semester. And so stick around in the next video or two. We will bring all those theorems together, review them all, and see how they can really all be situated in a larger context, and they can all be seen as a special case of something more general. So stick around for that one.